Algebra 2 notes. 8-4 Algebra of Complex Numbers. So we're calling this Complex Numbers Day 2. So we're going to build off what we learned about complex numbers yesterday. So first of all, standard complex form we learned was a plus bi, where a was our real part of the number and bi was our imaginary part. So like an example of an imaginary number was like 2 plus 3i. So we looked at numbers like that yesterday. If a is 0, and I meant to write equals, not equals, so let's fix that. If a equals 0, and b is not 0, I guess, then we have just a pure imaginary number, right? Because I would have no real part. If b equals 0, then I have a real number because I have no imaginary part. And probably the most important thing here is if I have a plus bi, and I tell you it's equal to c plus di, then that means my real parts are equal. So a equals c, and my imaginary parts are equal. So b would have to equal d, because both of those are being multiplied by I. I could write bi equals di, but when we divide by I, it's just b equals d. So we're going to use that in example 1. In example 1, they want us to solve for x and y, and we have two complex numbers. So when I am looking on the left, I have a 2x and I have a 3iy. So my real part is 2x. So the real part we like to write first, but we always want to look, right? This is a math problem. This isn't my final answer. But this is the part that's definitely real. It does not have imaginary number in it. On the right-hand side, I have 8 plus 12i. So the part without the imaginary number, the part without the I is an 8. So 2x is going to equal 8. And then I can go through and solve that. So I'm using that property that we just wrote down. If I have two equal complex numbers, the real parts are equal, and then the imaginary parts are going to be equal as well. And we're specifically going to write it as the coefficients of the imaginary numbers. So now I'm going to switch my colors, and my imaginary parts are the 3iy and the 12i. So I want to think about just those coefficients of I. So if I'm looking at this 3iy, I would say that 3y, because that's the part being multiplied by I, is going to equal to, on the other side, I would use 12. Divide both sides by 3, y equals 4. And then my last step is to write my answer as an ordered pair. So 4, 4. So next we're looking at the arithmetic of complex numbers. So you'll notice that between the parentheses in problem 2, we have a plus sign, and the directions also helpfully tell me to add. So when I am adding complex numbers, I just add the real parts and I add the imaginary parts. So 3 plus 8 would be 11. 5i minus 2i is a plus 3i. We're going to actually work down this page here. So what we're going to do is we're going to do 2, 4, and 6, and then you could try 3 and 5 and 7 on your own. Like pause the video after I try 2, 4, and 6, and then you could check your answers. So I'll work those out quickly without a lot of explanation. So in 4 it says subtract. So just like before, my minus sign gets distributed into the parentheses. So I really have 3 plus 4i minus 8, and then minus negative would be plus 3i. So I always want to add the real parts first because we want our imaginary numbers written as real plus imaginary. So 3 and negative 8 would be a negative 5, and then 4i plus 3i would be plus 7i. For 6, I want to multiply. So I have to go through and do all the multiplications. So 2 times 3 would be 6. 2 times negative 8i would be, minus 16i. 3i times 3 would be plus 9i. 3i times negative 8i would now be negative 24. And then I times I is I squared. So hopefully you're thinking about I squared from yesterday. So now I need to put, I'm going to go ahead and simplify my middle terms and to put those together. So negative 16 plus 9 would be a negative 7i, so 6 minus 7i. And then remember yesterday we found that I squared was equal to negative 1. So we said because the square root of -1 was equal to I, if I was going to square both sides, the square and the root canceled, and I squared was equal to -1. So now I'm going to make that substitution. So minus 24 times -1, which means I have 6 minus 7i plus 24. And then I would add my real parts and write those first. 6 and 24 would be 30 minus 7i. On our last problem, we're going to divide this out. And just like we don't like square roots in our denominator, we don't like i's in the denominator either. So I'm going to multiply by the conjugate. So remember conjugates from yesterday, we keep our real part, but we change the sign on the imaginary part. So in my numerator, 2 times 5 is 10. 2 times I would be 2i. 3i times 5 is going to give me 15i. And then plus 3i squared. In my denominator, you might recognize that we actually have what's going to be difference of squares because I have a 5 minus I and a 5 plus I. So I'm going to show distributing this all out, but you could actually just shortcut this if you understand how that pattern works. So 5 times 5 is 25. 5 times I is plus 5i. And then we have a minus 5i. And then minus I squared. So we use the conjugate on purpose, so we would have this plus and minus that would cancel out. So in my numerator and my denominator, I'm going to replace the I squared for -1, and I'm going to combine my like terms. So now I have 10 plus 17i. And then remember, I squared is -1, so this is a 3 times -1. And I want to replace the I squared in the denominator also, so I'll have 25 minus -1. I need a little bit more workspace on this problem. So 3 times -1 would be a -3, so I have 7 plus 17i. Hang on a minute. And then my denominator, 25 plus 1 would just be a 26. It is fine if you leave your answer this way. I am very happy with this year in math. But your book will take an extra step, and they're going to write this split apart as that real part plus the imaginary part. So they will write 7/26 plus 17/26 times I. So again, you can stop it right here, but I need you to know that those are equivalent because you're going to be checking your answers. All right, on my second one, I want to multiply by 4 minus I. So in my numerator, when I multiply, I have 12. And then let's see, minus 3i plus 8i minus 2i squared. I'm going to work this one a little bit faster. Denominator would just be a 16 minus I squared. I know there'll be plus or minus in the middle. And then the minus 3i plus 8i would be a 12 plus 5i. And I already know, I'm kind of showing work in here how I would normally show work, that I squared is a -1, so it's going to change the sign. Instead of a -2, I will have a plus. And this is over 16 plus 1. Remember, I squared is -1. So I'll have 14 plus 5i over 17. And you can stop there. Or we could write 14/17 plus 5/17 I. So I said that you could pause the video and then go back and check those other three. So I'm going to go ahead and work those out quickly right now. If you want to pause and try them yourself, please do that. So hopefully when you checked your answers, you had everything right, and hopefully I had everything right as well. I'm going to go ahead and move on to our next page. So we're looking at powers of I. So I by itself is just I. It's the square root of negative 1. We've already found that I squared is equal to negative 1. So I cubed, it makes sense, is going to be I times I squared. And we know I is just I squared is negative 1. So this is I times negative 1, which is negative I. So when I'm looking at I to the fourth power, there's different ways I could do this, but I'm thinking about how fourth power is really squared and then squared again. So if I take negative 1 and I square it, I get a positive 1. So now let's look at fifth power. So there's a lot of different ways to break these up. I could use 2 and 3. I could use 1 and 1 and 3. I mean, there's lots of ways to break up this power. But I think for me, the easiest way is to think of this as I to the fourth times an extra I. Because remember, this I would be first power. So I know that I to the fourth is 1. And then I to the first is just I. So this is going to be equal to I again. So that's kind of interesting. So on the next one, when I have sixth power, I'm going to write that as I to the fourth times I squared. So I to the fourth is just a 1, and I squared is negative 1. And so I to the sixth is just negative 1. So hopefully you're seeing a pattern now. I to the seventh is I to the fourth times I cubed. And I to the fourth is just 1, and I cubed is negative I. So I to the seventh again will just be negative I. So I hope you're really seeing a pattern now. We have I and I to the fifth, they're both I. When we look at I squared or I to the sixth, we have a negative 1. I did third power, seventh power, they're both negative I. So I'm going all the way through these answers all over again. So let's check the last one. So I to the eighth would be I to the fourth times another I to the fourth. So we know that I to the fourth is 1. So 1 times 1 would just be 1. So hopefully you get the idea now that if I did ninth power, I'd be back over to the same answer I got for fifth power and first power. These are cyclical. And using that power of 4 and kind of looking at what's left over is going to be probably our best option for solving these. There's a lot of different ways to work these out, but I find that students are the most successful look at taking out those powers of 4 and finding out what's left over. So the way I'm wording that might almost sound like when I say what's left over, like a remainder. And that's exactly what we can do. It turns out that we can take this power and we can divide by 4. So 4 times 3 is 12. And then my remainder is 3. So this is going to be equal to I to the third. So my remainder is going to end up being this exponent here. Because I know all those I to the fourths would just make a 1. So all I have to worry about is what that remainder would be left over after I took out all those fourth powers. Now I just have to look back. I cubed is equal to negative 1. Or sorry, negative I. So this will equal negative I. So one of the math problems or a math problem type that you're going to see a lot is us throwing these random powers of I at you, and then you've got to figure out how to simplify them. So we'll go ahead and take a look at 25. So 25 divided by 4 would be 6. And then subtract, my remainder is 1. So I to the 25th is going to be the same thing as I to the first, which is just I. So again, this remainder is going to go up, and it's going to be that leftover exponent. So 26 power, let's go ahead and do that again. 4 divides into 26 6 times. We're left with 2. And so again, this leftover, that remainder is going to be my new exponent. So this is going to be the same as I squared. And I squared is negative 1. On the last one, I have I to the 40th. And 40 divides evenly by 4. So if it divides evenly, if it's a multiple of 4, it's just going to equal 1. And I guess our property really still works because if I have I to the 0 power, anything to the 0 power would just be a 1. So these last four, we're just looking at some more advanced, just applying these ideas of complex numbers to be able to solve. So first I want to solve by factoring, and we did that yesterday. So normally in math, we would say, there's a plus, I can't factor. I don't have a difference of squares. I can't use that pattern. But we know that we could rewrite this now from our notes yesterday as 4x squared minus 49i squared. Maybe we should review why that is. Let's go ahead and review that. It's good to see things multiple days. So I'm going to rewrite the 4x squared as 4x squared. Instead of plus 49, I'm going to write minus a negative 49. And then I know that I could rewrite that as 49 times negative 1. And remember, this is still equal to 0. Negative 1 is equivalent to I squared. And now that I have a minus sign and two squares, I have the difference of squares I can factor. So 2x plus 7i times 2x minus 7i. And now I can do zero product property. So 2x plus 7i equals 0. 2x minus 7i equals 0. So when we're solving, we're getting the x by itself. So I know you're looking at that I, you're thinking there's two variables. How can I solve? But remember, I is something. It's defined. So I'm going to subtract 7i and then divide by 2. So x will be negative 7 halves times I. Remember, we always do the coefficient times I. Or my other answer would be x equals a positive 7 halves I. So on 11, we're going to solve by taking a square root. So I'm going to start by subtracting 4 on both sides. So it's nice we're getting a little review of chapter 4 as well, and all the different solving we had for quadratics. It's not going away. We're just building on that right now. So we're getting extra practice. And then I need to square root both sides. So when I have the square root of negative 4, hopefully remember from yesterday that that's just 2i. The square root of 4 is 2, and then if we have a square root of a negative, we have I. On my other side, I have an absolute value of x minus 3. To get rid of the absolute value signs, I get a plus or minus. So x minus 3 equals plus or minus 2i. And then I would add 3 on both sides. So x equals 3 plus or minus 2i. So for our last two, let's see, this one we're solving with the quadratic formula. So remember, we have to find a, b, and c. A is 2, b is negative 6, c is 5. So quadratic formula, let's see, x equals negative b, so that'd be a positive 6 plus or minus square root of b squared minus 4 times a times c, all over 2a. Make sure your square root goes over all that stuff. Fraction bar goes over all that stuff. Lots of places for mistakes on this. I really prefer to factor or complete the square. Working inside my square root, negative 6 squared is a positive 36 minus, let's see, 5 times 4 is 20, times 2 would be 40. So now we have 6 plus or minus the square root of negative 4. So that's why they're telling me in the directions to solve over the set of complex numbers. So this will be 6 plus or minus 2i over 2. And remember, we have to divide the 2 into both parts. So 6 divided by 2 would be a 3. And then 2 divided by 2 is 1. So 3 plus or minus I. This last problem, we're working backwards again. We're asked to find a quadratic equation that has these answers. So I'm going to start out by writing x equal to both of those answers. X equals 6i and x equals negative 6i. And then I am going to make both of them so that I have a factor of something that's equal to 0. So what I mean by that is like x minus 6i equal to 0. And the other one would be, if I add 6i to both sides, x plus 6I equals to 0. So this almost looks, hopefully, to you at this point, like zero product property backwards. So here's the parts where I had them set equal to 0, and then I had to add or subtract. There were the answers. So we're just working the whole thing out backwards. So if these two factors could equal 0 separately, then I am going to multiply them together and make them equal to 0. And then I need to go through and do all my distributing because this isn't the right form. I want it to be multiplied out. So x times x is x squared plus 6ix minus 6ix, and then minus 36i squared. So hopefully this is looking familiar. Middle parts cancel. Hopefully you knew that because one's plus, one's minus. We need to really identify with that structure for sum and difference and know how that works. So now I have x squared minus 36i squared, and my I squared is -1. So 36 times that -1 means I will now have x squared plus 36. So this looks a lot like some of the factoring stuff we've been doing, but we just kind of worked it through backwards. And it's equal to 0. That would be the other difference here. So this is the end of our day 2 complex number notes. So please make sure to ask questions in class if you need help. We will have a big complex number quiz after these notes. That'll be the next day, review and a quiz.